All right, so I'd like to start out by thanking the organizers. It's a great honor to give this lecture, and I'm also actually looking forward to learning about the center. Here, I must say I was not completely sure which audience to target, so as a result, I think my talk will be a little bit of a mix of kind of physics and technology and maybe of an outlook, and I hope very much that there will be something for everyone. So what this talk and this work is about what we sometimes call a quest for controlling quantum world. As many of you know, there is now a big effort to try to really isolate and control some very simple quantum objects like single photons, single spins, single atoms. And then once you succeed, start really building more and more complex systems from that. And there are two things we would like to do with these systems. One is we would like to start exploring new physics with this kind of engineered quantum many-body systems, which basically means creating and probing new states of matter. But then we also would like to start using these systems for new applications. And I guess now those don't need really much of an introduction. Say in the news lately, things like quantum processing, communication, and metrology. So my talk will be about how we are going about building this kind of new systems, but the examples I will give mostly will be this kind of physics examples, but I would like to emphasize right from the beginning that this new physics and new applications in this area really go hand in hand. So basically these directions are very closely connected. Now as most of you also know, this is actually an exciting time in this field, and you could call it a kind of an ultimate quantum rivalry, and this can be understood in many different ways. You could think this is a competition between different physical systems, who will be the first one to build a quantum computer, or maybe competition between different nations. But actually I would like to take I would like to step back here and take much kind of broader view, maybe a little bit kind of an Eastern type, philosophy view. So I would say that this is really a competition between two contradictory forces of nature. One is controllability, and another one is scalability. And if you think about that, you realize that this competition between forces is present not just in quantum physics, but almost all areas of human activity. For example, so if you have an organization which have a lot of smart people, let's say physicists, and if the size of organization keeps growing, right, eventually it will become very challenging to control this organization, right? And so this kind of stuff is present also in the domain of quantum physics. So as we basically start isolating the qubits and controlling the qubits, and then we start putting them more and more of them together, it becomes harder and harder to really keep this aspect of controllability. So, but what is exciting is that we are now just turning the corner. Several experimental systems are becoming large enough, controllable enough. And the current frontier in this field is really building the systems which can perform tasks which modern classical computers can really not do. And in practice, this actually means building the systems, of maybe 30, 40, or a larger number of truly coherent, controllable qubits. So I already mentioned that the first thing that we are already doing with the systems is studying new physics, and I'll just give you one example what kind of physics which we can actually explore with the system. So when we start studying these days even undergraduate physics, one of the kind of first classes in quantum mechanics, you learn about coherent evolution, and you learn that, you know, in quantum theory everything should be unitary, so if you time reverse it, the system should come back. And you know, experiments now can really, you know, perform this kind of evolution and time reverse, and, you know, it works as planned. But then the next, you know, semester, or even the same semester, you know, you take a class on statistical physics, and there you learn about things like equilibrium postulate, thermal ensemble, phases of matter, and these are intrinsically reversible things. So what's going on? What's the connection between these two? In particular, you could ask, you know, when does, you know, closed quantum system start, you know, behaving, you know, such that it obeys the laws of statistical mechanics? How does it happen? What's the dynamics? What's kind of the thermalization process? So these are actually kind of, you know, very basic, but it turns out really deep questions. So, and this really kind of goes under the name of understanding many body dynamics far from equilibrium, understanding the process of thermalization, understanding the role of localization, long-range interaction, and basically in this research what we hope to learn is we hope to actually discover some completely new states of matter which, you know, completely obey the law is completely different from the laws of kind of classical kind of, you know, new equilibrium or even quantum new equilibrium physics. And then, you know, if we can really discover and understand the states of matter, we hope that they also be useful for exploring these new applications, for example, quantum computing or quantum metrology. And I will give you a couple of examples from this kind of work today. Okay, so here's my plan. So I would like to first focus on a new approach to building a scalable quantum system. It will involve, you know, a little bit of material science, but it will be very kind of funky material, very unusual material, which we can really build atom by atom. And I can actually show you how we can build a system atom by atom, which is strongly interacting, and then actually use the system as a kind of a quantum processor. In particular, the example I will focus on today, it will be an example of the so-called quantum simulator, in which we will implement Ising type Hamiltonian, and we will kind of start exploring this Hamiltonian to realize, for example, and study quantum phase transitions, and to realize and study these non-equilibrium dynamics of the kind I just mentioned. And then towards the end of my talk, maybe is a little bit of an outlook. I will tell you about similar approach which we are pursuing with purely solid state systems, so in which case we will use atom-like color centers in solid state systems, and actually also show how we can start building kind of quantum matter from this kind of devices, and actually in this case nanophotonics will play a role, an important role. Okay, so that's a plan. So let me start first. So the first part of my talk will actually involve building quantum information processors based on cold neutral atoms in a gas phase. And there are many reasons to pursue that. You know, one of them is that the atoms in a gas phase, you know, can have excellent coherence properties. They can maintain quantum mechanical coherence for a very long time. And, you know, if you want an example why this is so, think about optical clocks. You know, optical clocks is perhaps the most precise measurement instrument at the moment that humankind has created, and, you know, it is based on these extremely long coherence times associated with neutral atoms. Then it's also easy to create large number of neutral atoms. So indeed, in this room, you know, we have actually a lot of atoms around us. So if each of them, you know, can be used as a qubit, you know, we could have a, you know, very big quantum computer, right? So I will also, since it's a talk, the symposium on photonics, you know, important feature of atoms is that can be strongly coupled to light. But, you know, basically you already realize that some of the challenges which this approach will be facing. And one is that the atoms in the gas phase interact generally very weakly, but then the other one is associated with this kind of, with the laugh that I heard what I talked about using the atoms in this room. The reason why we cannot build quantum computers from atoms in this room is that we can actually not follow each of these atoms individually. It's extremely hard. So what it really means is that these neutral atoms are generally hard to kind of isolate and control individually, at least if you want to have a large number of them. The single atoms, we know how to create. But, if you want to have a large number, it's challenging. So motivated by these considerations, a couple of years ago, we started kind of exploring a new approach for building quantum matter. And essentially, in this approach, we use something like a Maxwell demon, type, idea. And, it essentially involves removing entropy by observation. So specifically, the way how it works is the following. So we start with the gas of the pre-cooled atoms, pre-cooled using lasers, using conventional techniques which has been developed over the last 30 years or so. And then we shine the focused laser beam. So this is the so-called optical tweezers. The idea here is that atoms are polarizable, and they are, as a result, attracted to the point of highest intensity, to the focal point of this laser beam. Now we focus these tweezers very, very tightly, such that in each of these tweezers we can have at most one atom. Two atoms just don't fit together. So this is just one tweezer, but in our experiment we start with a large array of tweezers, about 100 of them at the moment. And what happens is that we just load these tweezers, but this loading is a random process. So in some tweezers will have one atom, and some tweezers will have none. And this loading process is completely probabilistic. So there is a lot of entropy in the system. So to get rid of this entropy, what we do is we simply take a picture of this loaded tweezer array, figure out which traps are full and which are empty, and just remove the empty tweezers and rearrange the remaining tweezers in any desired configuration. So it's as simple as that. Now we end up with the array, regular array of the atoms, which are spaced by, typically by about few microns. And then, of course, we need to somehow make these atoms talk to each other, interact with each other to execute, for example, quantum logic gates. And we're actually pursuing two approaches in my lab to do that. In today's talk, I'll focus mostly on this first approach, where we take these atoms and excite them into the highly excited Rydberg states. And so in the Rydberg state, the atom size becomes very large. And basically what it means is that the atoms start feeling each other's presence. So this will be the method I will mostly focus about. We also are pursuing the approach where the atoms are coupled to a nanophotonic system like photonic crystal, and basically this photonic crystal mediates this interaction. I'll maybe mention a few words about that towards the end of my talk. This kind of approach, both of these approaches turn out to be extremely powerful, and this is the basis for our collaboration between a Center of Ultra-Cold Atoms, between Harvard and MIT, between my group, Marcus Greiner's group, and Vladan Vuletic's group. So these are these two wonderful scientists. So just one picture of how our experimental apparatus looks. So we focus the laser beams in a vacuum chamber, but the key component of this apparatus is this device called acousto-optic deflector. So basically what this acousto-optic deflector does, it takes as an input just one laser beam and a number of RF tones, and then for each of RF tones the laser beam is deflected by a certain angle, and then what we do is we simply focus this kind of the output of this acousto-optic deflector and then focus it in this vacuum chamber, and then we have a second objective which we use to take picture of atoms and then basically activate this kind of fast feedback protocol to just rearrange and create an arbitrary arrangement of atoms. So this is at least the latest generation of the team of the people who actually build experiments. So basically I should say that this experiment was started, just to give you a sense, 3 years ago it was kind of an empty room, and actually Manuel Anders, who is now starting his own group at Caltech, was actually the first person to kind of start building that. And you will see now where we are. So basically, so here is now an illustration where we start with an array of 100 optical traps, and then load them in a way how I described. And basically, after the loading, what we do is just we take all full traps and then move them to the left. And what we see is that after this first image, which corresponded to this unordered traps, the second image is much more ordered. So basically, there's almost perfect. Almost every trap has something. Maybe there is one trap is missing here. So, of course, we can also create other structures. So here's, for example, clusters of 2, or oops, sorry, wrong. Or clusters of tens. And once again, these are all single-shot atomic images. So basically, it kind of indicates the quality of the preparation array. So for example, here is one atom missing, here is one atom missing, but it's only 2 atoms missing in this entire kind of sequence. So this procedure works extremely well. And of course, what we can do is we can also vary the geometry with each repetition, and then for a small contribution to Lukin Lab, we can write the name of your company. It's for industrial partners. So, okay, but at the moment everything is completely, totally classical. There is no we just create an arrangement of kind of classical atoms. Now we would like to use them as a quantum bits, and for that we need to enable some interactions between the atoms.
Will you say what atom it is?
Oh yes, sorry. No, I did not say. So we use in this experiment we use rubidium atoms. But the reason why I did not say it is actually kind of a fairly generic procedure. So it can be applied for a wide variety of atoms, so long as the atoms can be laser cooled, right? So rubidium is the most convenient from the point of view, is among the most convenient from point of view of laser cooling. But they actually, I will comment on why different atoms might be, kind of more interesting. So, okay, so at this point, we would like to enable interactions between the atoms, and we will do that by exciting the atoms coherently from their ground state to the highly excited state with large principal quantum number. This is a so-called Rydberg state. And the reason why we use Rydberg states is because they combine 2 key features. So on one hand, these Rydberg states have very long lifetime, and on the other hand, because the size of the atom in the Rydberg state becomes large, atoms in the Rydberg states have very strong interactions. So in particular, the interactions, van der Waal interactions between these 2 atoms grow as an 11th power of principal quantum number, and that means, for example, if you go to a state with n around 100, the interaction will be 14 orders of magnitude stronger than the interaction between the ground state atoms. So 14 orders of magnitude is a large number, and we can really make well, I was told to have a broad talk. So, so basically, we can make good use of these interactions. So one consequence of that is the idea of the so-called Rydberg blockade, which can be actually understood very simply in the following way. Suppose you start with 2 atoms. First, these 2 atoms are very far away, and suppose you just shine resonant light on both of these atoms. So both of these atoms will undergo the just resonant excitation, will undergo something like Arabi oscillations, and and they will be completely independent. But suppose now you bring them together, and then eventually, at certain distance between the atoms, this van der Waal interaction will take over, and what it simply means is that the state where both atoms are excited will be shifted in energy very, very rapidly. So what this means is that if you try to use, for example, a resonant excitation to excite both of these atoms, what will happen? You will be able to excite one of these atoms, every one of these atoms, but not both at the same time. So what this means is that the simultaneous excitation of 2 Rydberg atoms will be blocked, provided the atoms are closer than certain distance. This is so-called Rydberg blockade, and for typical values of Rabi frequencies and Rydberg levels, this value will be something like 10 micrometers. So kind of that's the idea of this dipole or Rydberg blockade. So the idea is that the interaction between Rydberg atoms blocks multiple excitations. So in fact, it generalizes to the situation where you have more than two atoms. So for example, if you have a little cloud within this blockade radius, so in this cloud you will be able to excite one and only one atom, but never more than one. So what this means in particular is that this entire cloud can sort of start behaving as a kind of a macro atom. So basically, where you only have two states available. One is all of the atoms in the ground state, and one is one atom excited. And of course, you can excite now each and every one of these atoms. And as a result, for example, the probability of excitation of this one atom will increase with number n, with total number of atoms, or in other words, the Rabi frequency, the characteristic coherent excitation rate, will increase the square root of n. And this will be kind of a characteristic feature of this so-called Rydberg blockade. Now, this Rydberg blockade, I should say immediately, is not a new idea. In fact, this was the idea which we theoretically developed together with Ignacio Chirac and Peter Zoller's group a long time ago. So I actually even thought about this experiment, as my kind of start. When I was starting at Harvard, I was thinking about doing this experiment, but at that time I thought it was maybe a little bit too complicated. But in the meantime, many groups have done it. There are many applications of that, ranging from many body physics to quantum information to quantum nonlinear optics. And the question is, can we combine this kind of idea with our atom array approach? So in order to do it, so we will make use of two photon excitation. So here the fact that it's a rubidium matters. So what we do is we start with atoms in the ground state, 5s state, and then with two colors of lasers excite them to the state with n equals 70. This is basically a Rydberg state which we'll work with. And for now, let's just excite these atoms homogeneously, for example, in the arrangement of the kind shown here. So, what we can do now, we can actually perform this experiment with several different types of atomic arrangements. One of them will be an arrangement where the atoms are just isolated, they are very far away. So in this case, we will just excite them and they will undergo Rabi oscillations. So they will go between the ground state atom, where there is probability of Rydberg atom is 0, and excited state atom where probability is 1, and this is just a classic Rabi oscillation. But then instead we can also do this experiment with atoms, with pairs of atoms which are sitting nearby, or with triplets of atoms, 3 atom groups. And what we see in each of these cases, we still have at most one atom excited in the entire group. But at the same time, the Rabi frequency, the Rabi rate actually changes. And this change follows exactly this kind of square root of n behavior, so long as the cluster size is smaller than the blockade radius. In this case, the blockade radius corresponds to about like 3.5 kind of separations between the atoms. And these Rabi oscillations are really the Rabi oscillations between the states where all atoms in the ground state and one of the atoms excited is a kind of symmetric, actually there turns out to be an entangled state. So basically this kind of Rydberg blockade works very nicely in this kind of atomic arrays. But once again, I would like to emphasize that this phenomenon has been observed. So you could ask what's new, and actually the new thing is that we can really, control now, this kind of Rydberg excitations and the interactions with very high fidelity. To just give you a little bit of a flavor, let's just now focus on the group of just 2 atoms which we excite into the Rydberg state. And so in this case, we are supposed to be able to excite just one Rydberg atom and then create this so-called Bell state. So basically it's a state where one Rydberg atom excited, you don't know which one, and there is a well-defined phase between these 2 states. So we can actually first characterize whether indeed this is indeed the case that there is only one excitation here, and actually it's very easy to see. So for example, this is the probability of 0 excitation, probability of 1 excitation, and probability of 2 excitation. What we see is that basically we can almost completely inhibit this 2 excitation probability. But then we also need to actually make sure that we create really a coherent superposition, in the sense that the phase here is very well defined, and we actually can do that by just applying a laser beam to one of these atoms and just kind of shifting its energy levels a little bit to induce a kind of differential phase evolution. And then what happens in this picture is that you basically start kind of evolving between this symmetric superposition into the asymmetric and back. And the way how we can check that this evolution takes place is we can let this evolution happen, and then at some point just try to de-excite the atoms back, and basically what will happen is that only symmetric superposition should be de-excited, anti-symmetric is kind of dark, right? And that way we can actually very easily measure this kind of parity of the oscillations, and actually from both of these measurements we can actually extract the entanglement fidelity, and actually this fidelity is actually quite high, is actually very close to 100 to basically unity, to 100%, and all of these kind of operations we can actually realize on a time scale of about 100 nanoseconds, and actually both of these values can be improved. So this actually really corresponds to very high fidelity quantum control of the system, even compared to sort of the best, the state of the art like trapped ions or superconducting qubits. Okay, so I gave you a little bit of the feeling of what is this kind of platform capable of doing. So let me now just talk about making it kind of more complex. In other words, increasing the kind of the system size, and that's kind of a unique advantage of this approach. And I will do it on an example of using the system as a kind of quantum simulator. So what is a kind of quantum simulator? The idea here is that I would like to implement some kind of complex spin model which you cannot easily describe classically in a well-controlled manner. So in fact, in our experiment we will implement this Ising type spin model. Is kind of a paradigmatic model in many-body physics, and specifically, we will implement this kind of Hamiltonian, which is shown here. So let me just describe different parts of this Hamiltonian. So this Hamiltonian pertains to a two-level system, which will be basically atom in a ground state and atom in a Rydberg state. So we'll be able to flip this. This will be our effective spin. So we can flip this spin with this laser excitation. So we also will have a term which is actually proportional to basically kind of magnetic field in the z direction, if you want, or chemical potential. So m here corresponds to number of atoms in a Rydberg state. So basically, this term acts as a kind of chemical potential of the system, and this corresponds to the interaction. And basically, our atoms interact only if both of them are in a Rydberg state. So basically, that corresponds to this kind of density-density type interaction. So let me just kind of focus on this Hamiltonian here and ask a question: what's the ground state of this Hamiltonian? So that way we can actually draw a phase diagram. So this axis here will be one is this detuning. Basically, it's like a chemical potential, and another one is effective interaction range. And so if we don't have any interactions, then it's very easy to see what the ground state of the system will be. So if the detuning is negative, in this case you don't want to have any atoms in a Rydberg state. So basically all atoms should be in a ground state. But if the detuning is positive, then you would just want to flip all of these atoms, right? This clearly will be a ground state of the system. But then, of course, there are these interaction terms, and for example, if we have blockade, we already have seen that it's extremely unfavorable to have both atoms excited in the nearby site. So in this case, what will happen, if a blockade is just a short range, kind of corresponding to nearest neighbors, you will excite this kind of state up, down, up, down, up, down. This is nothing but the antiferromagnetic state. Now, of course, what you can do, you can try to extend this blockade, and then in this case, you will excite every third atom. This will correspond to the phase in which Z3 symmetry is broken, or if you extend the blockade even further, every fourth atom will be excited, and then this kind of sequence goes on. So it actually turns out that this model has been extensively studied, in particular by my condensed matter colleague Subir Sajdev and collaborators, and actually it has this kind of very interesting phase diagram. So it turns out that basically if you change the parameter like a detuning and go from negative detuning to positive detuning, so these are all will be quantum phase transitions, and actually this quantum phase transition will be quite non-trivial. So this one corresponding to breaking Z2 order, the antiferromagnetic phase transition is very well known. It's an Ising phase transition, but the other ones are much more tricky. And so what we would like to do is we would like to now study this kind of phase diagram experimentally to first off kind of validate our approach, but also then maybe hopefully study and discover new things. And the first thing we will start doing is we'll start doing basically adiabatic following across the phase transition. We start with all atoms in a spin down and then try to go slowly, and initially let's look at the simplest case where we just have weak long range interaction. So what it means is that the interaction between nearest neighbor side will be much larger than the Rabi frequency, and the interaction between second nearest neighbor will be much smaller, will be basically negligible. So here is the experimental protocol. So we'll start with, we'll turn on our laser pulse, but we'll have a large negative detuning, and then try to go across this phase transition very slowly, and then eventually go into the ordered phase. And here we turn off the pulse and just take the picture of atoms. And the way how we take a picture is that we image the atoms in a ground state. So basically, whenever the atom is in a Rydberg state, we just won't see it. So what happens then is that if we start, for example, an array of 15 atoms initially in the ground state, then we undergo this transition, and then what we see is that every other atom is missing. That means that corresponds to basically every other atom being in the Rydberg state. So we can now basically study this process in various different ways. We can either just repeat it many times and study kind of average Rydberg probability. It still shows this up down pattern. Or what we can do, we can actually just follow each individual atom and change the tuning and then stop at different places and take a picture. And so here you also see the emergence of this kind of order, but you also see the region around zero detuning where there is a lot of fluctuation. So here is where this transition actually takes place. So clearly, okay, here we see this kind of Z2 broken symmetry, but we can also try to explore this other phases, and the way how we can do it is by either picking a different Rydberg state, with high n, that the interactions are stronger, or just shifting the atoms, closer, bringing them closer effectively, therefore increasing the interaction range. And that's what we have done here. So we just, this is a picture already showed, so we start with atoms spaced by a relatively large number. In this case, we enter the Z2 phase, but then if we, for example, start with atoms which are spaced, which are basically spaced closer to each other, then we enter this phase where we see that every third atom is missing, or in other words, every third atom is in a Rydberg state, or we can, bring them even closer, and we see enter the state with every fourth atom is excited, etc. So basically, what we see here is that we by programming our system, we can very easily pick which symmetry we can break. By just programming, for example, a distance between atoms, we can engineer the broken symmetry, and that's actually really tells you a little bit, already gives you a little bit of the glimpse into the power of this approach. Right? Basically, we can study different, variety of phase transitions in essentially kind of in a single, almost, well, not single experimental run, but in a single day. Okay, so so far, what I've showed you some kind of nice picture, but how do we know that our system is working well? So in order to do that, what we should do is some kind of bench marking, and what we can do is we can start with a small system, for example, in case of 7 atoms, 7 qubits. So this kind of system has sufficiently small Hilbert space that we can actually simulate its dynamics just on a classical computer, and we can compare our result of the classical, quantum simulation on a classical computer with our quantum simulation on the quantum machine. And what we see is, at this point, we see a very good agreement. So, for example, this is a many-body state overlap. So this is a system here starts in a state where all of the atoms are in the ground state, and then undergoes this transition, and then basically the state which emerges is predominantly is a 0, 1, 1, 0, 1, 0, 1, 0 state, this antiferromagnetic state. But of course, what we would like to do, we would like to now increase the system size and see what happens there. So, and we can go all the way to system sizes exceeding 50 atoms. And at this point, the Hilbert space dimension becomes 2 to the power of 51. So this kind of system you cannot simulate any longer on a classical computer, but we can do the experiment. And what we see, if we, for example, look at the ground state overlap, we see that this overlap decreases, but still for the 51 atoms, it's still reasonable. It's about 1%. So in 1% of cases, we get this kind of perfectly ordered state, up, down, up, down, up, down, up, down. But actually, what's even more interesting is that if you really now, repeat this experiment many times and basically look at the probability for each given state to occur. So most of the states, because there are so many of them, just occur just once. Some occur twice. But actually there is one state which occurs with highest probability, and this is the state with this perfect order, this up, down, up, down, up, down state. So I should also say that these are the results which we published at the end of the last year. It's actually since when we have not been exactly sleeping, so we've started improving the coherence of our systems and improving, for example, the phase noise of lasers, and actually we can now we can now boost this probability of creating a perfect state in this 51 atom system by about factor of 10 to about 10%. So the 10%, given is just huge Hilbert space, is a large number. So let me just kind of show you kind of another way how we can think about this system. So here is now single shot images. So we start with the atoms, with 51 atoms, all in the ground state, this perfectly ordered array. And then we perform this our evolution. And then in some cases, as I already told you, we will have perfectly ordered system, up, down, up, down, up, down. That's this last image. But in majority of the cases, it will not be like this. In majority of the cases, what we'll have is, typically the image is like this. So it's basically up, down, up, down, up, down, up, down. And then, you see here, there is some kind of, defect. So then another kind of ordered piece, and then another defect. So this is a kind of a classic textbook kind of, phase transition and kind of one-dimension picture. So basically, we have a long chain of ordered atoms, and then there is one defect. And what we can do now is we can just, look at these defects, analyze them. So we call them domain walls. We can basically, study, the average number of defects. We can study their moments. We have access to the full counting statistics of defects, and then, for example, we can plot this domain wall density or variance as a function of detuning of our chemical potential. And what we see here, is that the mean number of the defects actually smoothly changes from high to low, and while variance actually peaks. And this peak of the variance really kind of indicates the presence of the phase transition. So here the system does not know basically to which state to end up. So, and like these two states compete, and that's how we can actually really nail the point of the phase transition. So it actually turns out that for this Ising type transition, this predicted point is actually in a good agreement with the theory of Subir and coworkers. But we already see that one can really have kind of unique insights into the phase transitions using this approach. Just before kind of concluding this part, let me go back to this non-equilibrium dynamics, which I already advertised. So, you could say, well, okay, this is something like this kind of Ising phase transition, is something that, we all study, like this is, has been, described. Everything should be very well known, but actually, it turns out that when we did the first experiment, when we pushed the system very far away from equilibrium, we saw a surprise. And there are basically kind of two ways now we are looking at this dynamics. One is by using kind of near adiabatic evolution. So this actually here we study dynamics across the quantum phase transition, including these Kibble-Zurich mechanisms. Actually, these are not Kibble and Zurich. I realize now it's Peter Zoller and Subir Sachdev we are collaborating. Sorry. So, but basically, like this Kibble-Zurich mechanism manifests in many different ways. It can manifest in classical kind of phase transitions, but it also can manifest in quantum phase transition. Actually, this manifestation in quantum phase transition so far has not been, I would say, ambiguously detected. And actually, in our system, we can very easily not just verify this Kibble-Zurich scaling, but also now use it to study kind of more exotic transitions. But the thing which actually I would like to spend a few minutes is really, so this corresponds to kind of near equilibrium dynamics. But this thing that I would like to really spend a few minutes on is this kind of opposite case where we really kick the system very hard and just see how it relaxes. And here we really saw a surprise. I'd say we made maybe a small discovery here. So here is kind of the idea is very simple. So let's kind of go back to this picture that I already shown. So let's now pick the array of maybe 5 atoms, and then let's just kind of follow the trajectories, the excitation probabilities of all of these 5 atoms. Initially, we just adiabatically go across the phase transition and prepare this atomic state, up, down, up, down, up. So at this point, instead of just stopping, what we will do is we will change the detuning back, but now instead of doing it slowly, we'll change it abruptly. So that corresponds to essentially quenching the system, going across the phase transition very, very rapidly. So that way, you generically inject a lot of excitations, and what you would expect is that, okay, so you just, dumped a lot of energy in the system. It should relax and basically eventually, become, high temperature. So in this case would be an infinite temperature effectively system. And actually that's what in fact we wanted to study, but what we observed was actually kind of a little bit of a surprise. So what you see is that after you do this quench, you change basically this detuning to 0, just going just across the phase transition, what we observed is that somehow, this initial order disappears, but it kind of, the system has some kind of life, here. And, actually, if you just, zoom in a couple of points, so for example, here, it actually turns out that original order disappears, but then this kind of complementary order appears, down, up, down, up, down, up. Then you wait a little bit more, and then original order reappears, and this dynamics keeps going. So what's going on? Well, at this point you could say it's a very small 5 atom is not really kind of a thermodynamic system. Let's check it out. For larger system, it actually turns out that this phenomenon persists all the way if you go to the 51 atoms. So in this case you can characterize by looking at domain wall density. So initially it's low, right? You quench across the phase transition, it grows, right? It should grow to like 0.5, basically completely disordered system, but then, it exhibits this kind of oscillations. And the surprising thing is that, these oscillations are extremely robust. They have a frequency which actually does not naturally correspond to any kind of obvious, frequency. It's proportional to driving Rabi frequency, but it has some very non-trivial proportionality factor. But kind of the main surprise is that the system does not simply thermalize. And the reason is, the reason why it's surprising is that we are basically working with the many-body system, which is actually away from any kind of non-integrable point. And even under perfect blockade, it has a lot of states, a large Hilbert space to explore. And basically, what it means is it should just rapidly thermalize. It should thermalize on a time scale of maybe one of these cycles. So at the time when we first measured this, made this measurement, we were really quite puzzled. So we started doing theoretical calculations. We cannot quite simulate the system of 50 atoms, but we can do simulations up to maybe like 25 or so atoms. And indeed, what we observed, in agreement with experiment, is that when we were quenching this kind of anti-ferromagnetic state, we observed these oscillations, and here they also don't thermalize. Quite remarkably, if you start with another state, if you start, for example, with all atoms in the ground state, this quench results in just as expected in a very nice thermalization. And this basically phenomena were present either for constrained Hamiltonian or full Hamiltonian, including long-range interaction, excluding them. And actually what we also noticed while doing this simulation is somehow these kind of oscillations correspond to the fact that entanglement in the system is growing in a very kind of peculiar way. So basically what happens is that the nearby atoms become entangled very rapidly, but then entanglement spreads very, very slowly. And actually that's sort of what at the time our conclusion was, that these robust oscillations occur for certain initial states, and they are somehow associated with the slow growth of entanglement, which are likely due to this constrained dynamics. But at the same time, we really did not know what is going on. So this work actually stimulated a number of exciting theoretical studies, and I will just mention one example of them. So this makes a connection between our observation and the theory of the so-called scars in a chaotic system. So this can be very, very easily understood by just considering, for example, a billiard, which is an example of the chaotic system. So here, most of the trajectories of the particles, single particles, are chaotic. However, it turns out that in this billiard, there are few trajectories which are closed, like the ones shown here. So these trajectories are generally not stable trajectories, and you would say, well, if you now quantize the system, they should just go away. But actually, it turns out to be not so. So specifically, it was pointed out by my chemistry colleague Eric Heller a number of years ago that some of these closed trajectories have an associated kind of at least metastable eigenstates after quantization, and this is what he called quantum scars. So there are some conditions for these trajectories to occur, which correspond to basically the period and the Lyapunov exponent, but basically the bottom line is that this eigenstates really resemble classical periodic orbits. And basically, the idea of this work, which is work by Dima Abanin and his collaborators, and this is quantum many-body scars, is basically the states which are embedded throughout thermalizing many-body spectrum, which exhibit this robust dynamics. And actually, one can sort of think about those either in a kind of many-body state, or one can think about in some kind of semi-classical state. But actually, so we have now carefully examined this kind of this paper, and it looks like really that this quantum scar effect can really play the role. But basically, the bottom line here is that you already see is that once you start building a system which is large enough and coherent enough, some very simple experiments you can do on them really already lead to discoveries. Okay, so I think it's an exciting era in this field. And we have a lot to do. We're working on extending the system to 2D. probing entanglement, studying dynamics, thinking about error detection and correction. But maybe just one little thing that I would like to give you an example is that while I have focused, basically, on a physics application of these ideas, it turns out that there is very close connection between this work and a work on solving complex combinatorial optimization problems. Specifically, one very famous problem in this field is something which is called maximum independent set. So it's actually very easy to understand. So suppose you are given undirected graph which have some vertices and links, and these vertices are connected in some way through the links. And an independent set is just a set of these vertices which you color in such a way that none of the two connected vertices can be colored simultaneously. And so this is one independent set, so this is another independent set, and this problem, this so-called MIS, maximum independence problem, simply consists of finding largest independent set. You would say, well, it's an easy task, but actually it turns out that it's one of these NP complete problems. Actually, it's a sharp, it's NP sharp, so it's actually one of the hardest kind of problems of this set. So, and of course, for small system, you can just look at this graph and figure out that this is maximum independent set. But for large system, it becomes very, very hard. So it actually turns out that this problem is not only mathematically kind of important, but it's also practically important. So specifically, if you consider some subset of these MIS problems on these so-called unit graphs or unit disk graphs. So the idea here is that you have this kind of network of these vertices, and then you just connect them within a certain distance. So this also corresponds to a maximum independent set. So it's a specific case, but actually, a resulting network looks like this. So that's something that you probably have seen already. For example, at the back of your in-flight magazine, and this, that means that it's a really, this is a practically important problem. It's still an NP-complete problem, and actually important in design networks, machine learning, and stuff like that. So now, if you carefully listen to my to the rest of my talk, you will realize that this Rydberg blockade problem is actually very closely related to this kind of maximum independent problem. So specifically, once you go into this, kind of ordered state, once you change the, make the tuning large and positive, the ground state of the MIS problem coincides with the ground state of this Rydberg blockade Hamiltonian, where D is just a blockade radius. And so these kind of connections can really be now exploited. So for example, if you go and try to adiabatically, evolve into the ground state in a model of this kind, or try to use some more sophisticated techniques like approximate quantum optimization, these are the kinds of things which we really would like to explore. And in order to do it, we have to extend our system. We have to go from one-dimensional arrays to two-dimensional arrays. So far, we just used one acousto-optic deflector, but we can, of course, use two acousto-optic deflectors, and we're already starting to produce these two-dimensional arrays, and we're starting also, rearrange the atoms in this two-dimensional array. And so this actually, you can kind of see how, this, optics, many-body physics, and, quantum computing, quantum optimization are really converging. And maybe one thing that I would like to actually, given that there is a lot of industry, optics industry folks here, I would like to actually point out that optical technologies, in particular, the ability to produce large number or rapidly switchable laser beam, will be absolutely the key to the success of this kind of approach. So basically, this number of laser beams will, limit things like scalability, for example, and essentially, eventually a number of traps. All right, so let me switch gears here, maybe just last 5 minutes or so, talk a little bit about another approach which we are also exploring. And here I'd like to ask a question. Okay, so here I've shown you how we can basically work with the atoms in the gas phase. Can we do something like this also with solid state systems? And the specific focus, what I will do here is I will focus on these atom-like impurities in wideband gap semiconductors, which were basically systems like diamond, for example, which is now being used for many different applications, from quantum computers to biological sensors. And the idea here is that kind of the general philosophy's aim is to combine the best of all worlds. So on one hand, make use of this excellent coherence of isolated atomic systems, and at the same time kind of involve strong interaction, integration, and eventually maybe kind of large-scale scalability of the solid-state systems. So one example impurity that is perhaps the most popular in the set is the so-called nitrogen vacancy color center in diamond. So this constitutes of nitrogen atom, which substitutes a carbon atom in diamond lattice, and vacancy is basically a kicked out carbon atom, and between them, they form a stable, basically atom-like defect, which can be thought about like nature's own trapped atom or trapped ion. So in what sense? Well, on one hand, it can be addressed optically. So for example, if you look under reasonably pure diamond under a microscope, and you will kind of, you see those individual, dots. So this maybe could be thought as maybe kind of something like a stars in Ithaca sky at night, But actually, these are individual atoms kind of embedded in diamond. And in addition, they also have non-trivial ground state properties. In particular, there is a spin state which actually can be manipulated with microwaves, and it can be polarized and detected optically, much like I've shown you in the case of isolated atoms. But most importantly, this spin degree of freedom can also be long-lived. It can have millisecond coherence even under ambient room temperature conditions, and this is actually a kind of work that, some of the pioneering work that Greg was also involved while in the group of David Ashalom. So, but we would like now to not just look at single defects, but we would like to look at arrays. And this is an attempt to create an array. So in this case, you start with the diamond substrate and then just implant nitrogen ions. So in this case, what you see is that you can create a kind of a regular array, but you also see some limitation. For example, so clearly this array has some defects, and it's not as easy in this case to kind of rearrange the impurities to remove these defects. But even more significant, even if perfect array is created, so this is a solid state system, and so basically, if you start looking at each of these guys individually, you will see that, for example, their frequencies will be different. The frequencies will change in time, and that's a huge advantage of this atomic system. So in atomic system, once we were able to do 2, we immediately were able to go to 50. Here it's much, much harder. So, but we've realized this already some time ago and started thinking how to circumvent this. And one discovery that we've made a few years ago is that it turns out that you can circumvent some of these problems by invoking some kind of fundamental symmetry argument. So specifically, if you just replace nitrogen by a larger atom, for example, like silicon, so what will happen is that this atom will not be able to quite sit in one of these empty lattice sites, but instead will reside in between 2 lattice sites. So in this case, this is actually a substitutional impurity, rather, it's an interstitial impurity rather than substitutional impurity. And you would say, well, it's not a big deal, why should it matter? It actually turns out that it has huge consequences. And one of the consequences is that, those silicon vacancy centers turn out to be much more homogeneous and much more stable. And the reason is very simple. So, this system has the so-called inversion symmetry, and as a consequence, in both ground and excited state, the system has a zero dipole moment. And this is exactly opposite to the case of NV center, where it has a non-zero dipole moment. So what it immediately means is that these transitions are insensitive to a leading order, to the electric field, and they feature suppressed spectral diffusion. They feature suppress inhomogeneous broadening, and basically what it means is that if you start in a reasonably good diamond sample and just look for, pick two random silicon vacancy centers, what you see is that their lines are really pretty much lie on the top of each other. So like a lot of these, challenges are circumvented. Now, can we make them interact with each other? And one way of doing that is to use the fact that it's a solid state system, basically integrate them in some kind of nanophotonic device. So for example, one could start with something like a 1D photonic crystal where the light is confined to sub-wavelength dimension, and basically just, put a lot of these, impurities, and then use this photonic crystal to basically mediate the interaction between them. And that's kind of the approach which we decided to take, and this is a work now in collaboration with Marco Lonkar, my colleague in electrical engineering, and Hun Kun Park in Harvard chemistry. So here is how these experiments work. So we fabricate the devices like this from diamond. This is photonic crystal with a waveguide. So and now here in the photonic crystal we define a nanocavity, and in this nanocavity we implant via focused ion beam silicon atoms, and actually in this case we implant about 5. The resulting thing is about 5 silicon vacancy centers, which are implanted with pretty good precision. And then we basically interrogate this kind of device by bringing a taper optical fiber and basically, sending, light through this fiber and getting, light kind of out at a level of single photons with pretty high efficiency, routinely above 70%, in some cases we can push it to above 95%. So this are the group of the people who really kind of pushed this approach over the last few years. So let's just see how these experiments work. So we first start with just kind of an empty cavity. This is, for example, a cavity transmission line, but then we tune this cavity close to the silicon vacancy center line, and what we immediately see in this case is that this cavity transmission is modulated by this kind of peaks. So these peaks, each of them is due to the individual silicon vacancy center, and for example, if we zoom on these 2 peaks, on resonant peaks, we see that at resonance this silicon vacancy centers basically attenuate the transmission almost all the way to 0. Also, these lines here are broader than the lines for those which are off resonance. So it basically from here we can extract, for example, the Purcell factor or cooperativity is kind of a figure of merit of how strongly silicon vacancies interact. With cavities is 30, is very high. And we can also look at some of these off-resonant silicon vacancy centers, and in this case, we see that these lines are actually quite a bit more narrow, but also what we see is that instead of attenuating a transmission, they enhance a transmission. And actually that's kind of due to the fact that away from cavity, what happens is that this atom-photon interaction results in this kind of atom-like polariton. In other words, basically, one can think about this resonance as being due to the atom-photon bound state where silicon vacancy is dressed by the cavity photon. So the idea to create interactions between these two is just start with these 2 off-resonant silicon vacancy centers. So in this case, they cannot emit into the cavity mode directly, but they can actually exchange the excitation. One of them can emit a photon and one of them can absorb, and this exchange will occur at a certain rate, which is proportional to the coupling to the cavity squared divided by the tuning. And actually this signature of that interaction will be a formation of 2 split states. One of them should be more strongly coupled to light, this so-called bright or super radiant state, and another one will be asymmetric or dark or sub-radiant state. And to see that, what we do is we make use of the silicon vacancy spin states. We start with two silicon vacancies, and we can either prepare them in a state where one of the two only is coupled to a cavity, or both of them coupled. So if one of them is coupled, then we can just see the resonance associated with one of them. If another one is coupled, you can see the resonance associated with the second one. And now what we can do, we can, for example, magnetic field to actually just bring these two silicon vacancies into resonance with each other. And what we see here very nicely is that these two levels cross. And this is because only one of the silicon vacancies at this point is coupled to a cavity resonance. But if we couple them both, then what will happen is that these two resonances will get modified, and they're modified in a very special way, like shown here. In particular, if we now start changing magnetic field, what we see is very nice level anti-crossing, where actually one resonance becomes very strong, it's a bright resonance, and another one is basically almost kind of vanishes here. That's one of this is dark subradiant state, and this is very nicely in agreement with the theory. And basically, it shows you that we can now start really engineering interactions between the solid state emitters and the cavity. So I think I've used up my time, but I hope that this last piece kind of indicates both an opportunities but also challenges we are facing in kind of going from these atomic systems to solid state systems. We certainly hope, and I'm convinced that this generation of students will start experimenting with more than just two emitters, maybe with tens of them, and we have some ideas how to, for example, build networks on a chip and also kind of more long range. So we're also thinking about creative ideas like using, for example, effect of topology to circumvent the imperfections and disorder. But apart from these photonics applications, these atom-like centers can also enable other cool things, and I don't really have time about that. But one other part of our research program deals with using this kind of arrays of these emitters applied to quantum metrology, and actually they can do really, enable really cool things like looking at magnetic resonance imaging of single molecules, or examining two-dimensional materials layer by layer, or even looking at how worms kind of develop. But this may be a part of a different talk. So I've used up my time already. So I hope I convinced you that this is an exciting area where optics and photonics will play a big role. Thank you very much for your attention.
Questions, comments? Yeah. Should we let a student go first? Or I guess can I? Yes.
Does the entropy reduction scheme prohibit you from going to 3D? And do you even want to go to 3D?
Yes. Basically, like most of my talk was clearly 1D. So going to 2D is relatively straightforward, and we already are starting to do that. It actually is possible to go to three-dimensional system, and in fact, the group of Antoine Bravais I mentioned, there was some references to some of their work, have actually succeeded in rearranging atoms in 3 dimensions. So it's a little bit more challenging, it's a little bit slower, and there could be some applications for which 3D would be extremely useful, like for example metrology, where you want to use a lot of atoms. For things like quantum computation, quantum simulation, there is a lot to do in 2D already. So that maybe, in that sense, maybe is not as critical.
My question is about something that you didn't say. Yeah. So this IRG is particularly interested in fractional bosonic states and things like that. Yeah. Could you say a little bit about your work on the stuff that you just alluded to?
Yes. So this is actually maybe kind of corresponds to this one little picture here. So basically, so there is as most of you know, when we deal with electronic phenomena, topology can really help to to make certain effects extremely robust. Examples are, for example, quantum Hall effect. So the question is, can we actually extend these effects to the photonic systems? And there are a few challenges here. One is, first off, you need to have, you need to break time reversal symmetry. And it actually turns out that in systems involving, for example, when atoms and light are strongly coupled, is not so hard, right? Because atoms can, you apply a magnetic field, you break time reversal symmetry for atoms, and if somehow photons inherit this, that's actually that's okay. So the more of a challenging, task here is that these photons, they're not like electrons, so they can basically be easily scattered outside of this, for example, two-dimensional system. And for this reason, it is not immediately straightforward that a lot of these topological ideas can really be extended, to provide real robustness. But actually, it turns out that if you start with an atomic array and the distance between the atoms is actually smaller than the wavelength, than half of the wavelength, it turns out that it is possible to create some of these topological states where inside this 2D plane, this kind of normal, time reversal symmetry breaking, provides a robustness against the backscattering. But at the same time, these photons cannot scatter outside of these 2D planes, and this is due to subradiance. So this kind of little, disappearance of this two-atom resonance, which I showed, in the previous, is a kind of a toy model of that, So, okay, so in order to do it, we need to create large arrays. If you really want to make it robust, you should also have nonlinearity at the quantum level. So these are, some ingredients of that we know how to do, but of course making this entire thing will be kind of challenging, right? Sorry, it's a long answer.
So in the quadratic arrays, since you are able to observe, say, the Z2 or the Z4 phases, and presumably without changing it, so that part of the Hilbert space, which is what is the order, is not truly quantum. Is that correct? Because or is it not? Because you're observing it and it stays that way.
No. So okay. So in these specific cases, basically, for large negative detuning or large positive detuning, the ground state is kind of trivial, right? So in one case, all atoms should be down. In another case, you should have this kind of, simple kind of classical order. So what's quantum here is really this transition. And this transition is actually, turns out, like the competition between these two orders is really driven by quantum fluctuations. And that's what's kind of interesting, right? So, but, if you think about, for example, these optimization problems, here also the answer eventually is classical number, right?
Right. So I understand. Yeah. Thank you. So my question was, if you sit in Z2 and because you're able to observe it without destroying it, so you are still in a classical mode in one particular phase.
Well, okay. So it kind of depends, So sometimes you have to break the symmetry between, up down, and down, up, But but it's a kind of a very simple. It's a very simple symmetry that you break. So it is basically Once you are here, everything is classical. Once you are here, it's everything classical. But here in between, this is where kind of magic happens, right? It actually can be extremely non-trivial. And for example, if you start looking at excitations, this becomes extremely non-trivial. So this is,
Carl, you presented continuous quantum phase transitions. Do you encounter discontinuous transitions as well?
So so these are kind of second order phase transitions. So it actually, so there is kind of, it is a very good question, but so and it turns out, so if you go, so basically you need to introduce some kind of disorder or some frustration to observe something like what you are suggesting. So in particular, for example, in between these Z2 and Z3 ordered transitions, there should exist some region corresponding to the so-called incommensurate phase, where the Z2 and Z3 are competing. So in that case, this transition is not kind of this very nice, clean second order. It's actually more of a Claustrowitz-Taulis type, so things actually, start, like things close, gaps close exponentially. And, that's actually in the spirit much closer to this kind of disordered kind of network. It's actually kind of a, some kind of toy model, if you want, of this. And of course, these are extremely interesting, and for optimization, these are the ones which we really need to look at, So in a way, we are still warming up here. We already started looking at the one which I already mentioned is incommensurate, and it's actually very, very interesting. So the way how we study these things is we vary the speed with which we ramp, and we look at number of excitations. It's kind of this Kibble-Zurich measurement, and that actually turns out to be a very nice probe, Yeah.
Greg.
So thank you for an inspiring talk. So you showed that you could do kind of phase coherent entanglement between two atoms using this mechanism. What are the challenges to bringing kind of coherent quantum computing to this system implemented in that way? Is that something that you foresee as possible? Is it just a technical challenge, or are there other obstacles?
Okay, so what do you mean if you say coherent quantum computing? My question is, what do you mean exactly?
You're doing, 1-2-qubit gates to do universal.
So the question is, can you build a universal quantum computer using this approach? So the answer is yes, in principle. So in order to do it, you need to, of course, control each atom individually. We already have a control over the kind of Z rotation, if you want, rotation around Z-axis. So we do not have individual control over kind of each individual Rabi frequencies yet. But there are two caveats here. So first of all, if you want to solve interesting problems, for example, these optimization problems, either adiabatically or even non-adiabatically by using these gates, this individual control is not always needed. Some level is needed, you need to program these interactions, but you don't need necessarily to program individual Rabi frequency. That's one answer. The second answer is, I should come back and say that, okay, so at the end, this approach, how well it will work and how well it will scale, will depend on how well we can produce, say, thousands of beams of light, which are, which we can kind of rapidly switch, right? And that's actually the main limitation in terms of this kind of individual addressing. So basically, in order to individually address, in principle, it's possible. But, for that, we would need, in our case, 51 kind of individual control, but on a fast time scale. So on a slow time scale for atom rearranging, we already have it, but it's slow. So we want to make use of the fact that we have potentially here a gigahertz speed, and that such technology does not yet exist. And it will be critical for, I would say, any platform which involves optical manipulation.
Yes.
So the graph optimization problem you mentioned is also being addressed by quantum annealing architectures, I believe, too.
That's right.
So I was wondering how trapped atom approach
that's right.
Because it seems like that would be more scalable.
Yes, okay, so by quantum annealing architecture, you mean in particular like a D-wave machine. Okay, so the difference, there is, there are several key differences here, but the number one difference is that this approach is really fully quantum. So here we can do the entire evolution. In what I presented you, we do entire evolution for entire 50-qubit system from one state to another with making less than one mistake in the entire array on average, right? And that's why we can actually create this ground state with reasonable probability, right? For the D-wave machine, even with a single qubit, they would not be, so their coherence time is just way, way too short. So it kind of goes back to the question whether the D-wave machine is quantum at all, right? So that's kind of, that's one key difference. Well, it's perhaps the key difference. But so in addition to to this kind of adiabatic algorithm, what we can, of course, also we can explore non-adiabatic trajectories. We can actually do gates, and actually that way one can start exploring a larger sort of Hilbert space. So there are, for example, algorithms such as QAOA, which believed to be very promising, and things like D-wave machine, just in principle is not capable of doing that. Right?
Maybe one more. Good discussion, but we can go ahead.
Okay, thank you. When you use laser beam to promote atom from its ground state to elevated state, what happens to the electron within that atom? Just basically.
Which happened to the electron?
With the electron with that atom. Basically, what's the difference, from ground state to an elevated state?
Yeah.
And from basic physics.
Yes. Oh, yes. So that's actually a very good question. So you could say, let's take a step back, and we were talking about this, having no entropy, everything is perfectly controlled, low temperature. But when we shine a laser beam on this atom, and this atom goes from its ground state to state, say, n equals 70, there is a huge energy, right? So, and you would say, wow, this, this should be an extremely unstable situation, right? But it's actually not so. So first of all, when we make this transition, we do it very gently. We shine highly coherent, extremely pure, extremely narrowband light, right? And it goes back to my kind of comment about this where the optical technology really here plays a role. So we use the light to excite this Rydberg atom of the same kind which is used to make the world's best atomic clocks. So it should have really very low phase noise. And that way, when we do it, this is really like a quantum mechanical problem. We actually don't, we don't add entropy to the system, right? It's highly coherent, so we can promote the atom to the excited state, maybe stop halfway, and then bring it back. There is nothing deposited. So it's extremely, but that is only possible when the lasers which are used are extremely coherent, extremely narrowband, have very low phase noise.
All right, so if you have other questions, please talk to Mikhail afterwards. So let's thank him again. And we'll go on to the next speaker.